Have you ever wondered what drives the compass needle to point north? It's all due to a fascinating and unseen force, Earth's magnetic field. This invisible shield was first discovered in the 16th century by William Gilbert, an English physician and scientist. Yet, even after 4 centuries, it continues to be a subject of mystery and intrigue. This magnetic field does more than just guide our compasses. It plays a crucial role in making Earth habitable, supporting life in more ways than one. For instance, it helps birds navigate during their long migratory journeys and protects all life forms from harmful solar radiation by deflecting charged particles from the sun. Picture it as our planet's own superhero, silently and invisibly guarding us from the perils of the cosmos. Intriguing, isn't it? But how does this magnetic field come into existence? Our planet's magnetic field is a result of a fascinating process called the geodynamo. This theory dives deep into the heart of our Earth, to the core, which is primarily composed of iron and nickel. These metals are not just sitting idle, they are in constant motion, creating a magnetic field that envelops our planet. Now you might be wondering, how does the movement of these metals generate a magnetic field? This is where the geodynamo theory comes into play. The theory suggests that the magnetic field is a result of the movement of electrically conductive fluid within the Earth's outer core. The outer core, being a fluid layer, is subject to convection currents. These currents are caused by the heat emanating from the inner core, which is hotter and under immense pressure. The heat from the inner core causes the fluid in the outer core to expand, become less dense, and rise. As it cools, it sinks back down, creating a continuous cycle of movement. This convective motion of electrically conductive fluid coupled with the Earth's rotation generates what we call the geodynamo. The Earth's rotation plays a crucial role in this process. As our planet spins, it causes the convective fluid in the outer core to move in a spiral pattern. This spiraling motion, also known as the Coriolis effect, is what helps to organize the movement of the fluid into a coherent, planet-wide magnetic field. The geodynamo is not a static process, it's dynamic and ever-changing. The flow of the molten iron and nickel in the outer core is turbulent and chaotic, leading to fluctuations in the strength and direction of the magnetic field. So it's the spinning molten core of our planet that serves as a colossal dynamo, producing this magnetic field. But how exactly does this work? The mechanism of the geodynamo is an intricate dance of heat and motion. Picture the Earth's core, a sea of molten iron, hotter than the surface of the sun. This extreme heat causes the molten iron to move in a process known as convection, similar to the bubbling you see in a pot of boiling water. The heat from the core rises, while the cooler material sinks, creating a constant churning motion. But the Earth's rotation adds a twist to this motion. As our planet spins, it subjects the molten iron to the Coriolis force, a phenomenon that causes the moving fluid to curve rather than move in a straight line. This force shapes the convective motion into spiraling columns, aligned along the Earth's rotational axis. Now remember your high school physics? When a conductor, like iron, moves in a magnetic field, it generates electric currents. So, inside our Earth, as the molten iron swirls, it creates electric currents. And, as we know from the rule of electromagnetism, where there's electric current, there's a magnetic field. This magnetic field is amplified and maintained by the continuous motion of the molten iron, creating a self-sustaining dynamo. But the story doesn't end there. The generated magnetic field further influences the flow of the molten iron, affecting the electric currents and, in turn, the magnetic field itself. This feedback loop, the interaction between the magnetic field and the flow of molten iron, is what sustains the geodynamo. It's a complex process where heat and rotation drive a cycle of electric and magnetic creation, each influencing the other, all happening right beneath our feet. It's a dynamic system, a cosmic dance, choreographed by the laws of physics and the heat within our Earth. This self-sustaining cycle is what keeps our magnetic field alive and kicking. The geodynamo, the heartbeat of our planet, silently shaping and shielding our world from the harshness of space. But did you know, the Earth's magnetic field is not a constant? It seems stable, steady, like the reliable compass needle pointing us north. But in reality, it's anything but. It's dynamic, changing, and at times, it completely flips. This phenomenon is known as a geomagnetic reversal, a polarity flip where the Earth's magnetic field changes its orientation. Now you might be thinking, wait, does the Earth suddenly spin in the opposite direction? Not quite. The planet keeps spinning just as it always has, but the magnetic field itself flips. Imagine if your compass needle suddenly swung around and pointed south instead of north. That's a taste of what a geomagnetic reversal would be like. So how do we know this happens? We find evidence in the geological record in the form of magnetized minerals. As molten rock cools and solidifies, these minerals align with the Earth's magnetic field. Over millions of years, this creates a record of past magnetic fields, a bit like a tape recording of Earth's magnetic history. And what we find in this record is fascinating. We see that these flips have happened many times throughout Earth's history, roughly every 200,000 to 300,000 years. But don't worry, the last reversal was about 780,000 years ago, so we're not due for another one just yet. But when it does happen, it's not a sudden flip. It's a slow process, taking thousands of years to complete. During this time, the magnetic field weakens, even disappears altogether, before slowly re-emerging with the opposite polarity. And during this transition, our compasses would behave quite erratically. So what causes these flips? We're not entirely sure. It's one of the great mysteries of the geodynamo, the process that generates our planet's magnetic field. But what we do know is that these flips are a normal part of Earth's magnetic behavior. Yes, north becomes south and south becomes north, a magnetic flip. It's a fascinating reminder of the dynamic and ever-changing nature of our planet and its magnetic field. So, why should we care about the Earth's magnetic field? Well, let's start with the big picture. The magnetic field is a silent guardian, a protective shield that cocoons our planet, deflecting a significant portion of the harmful solar and cosmic radiation that bombards Earth every moment of every day. Without this protective field, the radiation would strip away the upper atmosphere, including the ozone layer that protects us from harmful ultraviolet rays. So, in simple terms, the magnetic field is a life preserver, a key player in making Earth habitable. But its role isn't just about protection. The magnetic field also plays a crucial part in navigation. For centuries, mariners have used the magnetic field to navigate the vast oceans. Even today, compasses, simple or sophisticated, are fundamentally reliant on Earth's magnetic field. Without it, getting from point A to point B would be a lot more complicated. And it's not just humans who rely on this magnetic guidance. Many animal species, from sea turtles to birds, use the Earth's magnetic field for navigation. These creatures undertake vast migrations, traveling thousands of miles with remarkable accuracy, guided in part by the magnetic lines of our planet. In a more modern context, our technology too is deeply intertwined with the magnetic field. Satellites, GPS, power grids, all depend on the stability and predictability of the Earth's magnetic field. Any significant changes or disruptions to the field could have serious implications for these systems. And let's not forget something as ubiquitous as the aurora borealis and aurora australis, the northern and southern lights. These stunning natural light shows are a direct result of solar particles colliding with our atmosphere, guided by the magnetic field. So in essence, the magnetic field is far more than just an invisible force. It's a protector, a guide, a facilitator of life and technology. It's a testament to the intricate and delicate balance that makes life on Earth possible. Without it, life as we know it would be drastically different. So we've journeyed deep into the Earth, right to its core, to understand the mystery of our planet's magnetic field. We've navigated the intricate science behind the geodynamo theory, which explains how the Earth's magnetic field is generated. It's a fascinating interplay of molten iron within Earth's outer core, creating electric currents that manifest as the magnetic field we experience. We've also explored the intriguing phenomenon of geomagnetic reversals, where the Earth's magnetic poles have flipped numerous times throughout our planet's history. It's a process that's still not fully understood, but one that certainly adds to the enigma of Earth's magnetic field. And finally, we've appreciated the significance of this magnetic field. Not just a cosmic compass, it's a protective shield, guarding us from harmful solar radiation and making life as we know it possible. Amazing, isn't it? The next time you use a compass, remember the incredible science that's driving that tiny needle to point north?